Hello there, this is Mrs. Carivo over at Frost Junior High, and we are starting Unit 3 in 9:30. We are going to talk about systems. So in our very first lesson about systems of equations, we are going to start by talking about how to solve linear systems by graphing. We will, included in that, we will talk about what on earth a system of equations is and how to figure out what solutions are, as well as using graphing in order to find some of those solutions. So as a warm-up, since we're talking about linear equations again, here's just a link back to Unit 2, what we just finished up, and making sure that you remember how to graph linear equations. So go ahead and pause your video and graph this equation. All right, so the first thing that I notice is that this equation is not in slope-intercept form. So I usually put my equations in slope-intercept form to graph them, and this one you probably could have tried using intercepts, but I'm noticing by the numbers that I think if I used the intercepts, I would end up with a fraction, and that's tough to put on this itty-bitty graph. So we're going to try and put this into slope-intercept form. So again, that is y equals mx plus b. So we're getting the y by itself. We're isolating that y. So if I'm trying to get y by itself here, then I'm going to subtract 3x first. I'll have negative 2y equals negative 3x plus 10. And then I'm going to divide every single term by negative 2. They cancel on the left, so I have y equals negative 3 over negative 2. Do negatives make it a positive, so it will be positive 3 halves x. 10 divided by negative 2 gives me negative 5. So then again, remember what I need from this equation is the slope. So my slope in this problem is m equals 3 over 2, because that'll be my rise over run. And then I also need the y-intercept, the b, and I notice in this equation my b will equal negative 5. And if we remember back to Unit 2, we always begin our graph with b, so I'm going to start at negative 5 on the y-axis. There we go. And then from there, I'm going to count my rise over run. So I'm going to rise 3, 1, 2, 3, and I'm going to run 2, 1, 2. And I'm going to do that as many times as I can till I get a line that goes all the way across my graph. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. There we go. And now remember, we could always go backwards. It could be negative 3 over negative 2, which would still give me a positive slope. So I could go down 3 and left 2. And one more time, and then I can't get any more points on the graph. So there's my nice straight line, and now I'm going to draw the line right through those points. I have a handy-dandy ruler here on my screen. You could get yours out as well. We are going to need them for this lesson. Ooh, see if I can line it up. All right, that'll get me close anyways. And I draw that nice straight line all the way through the points, and then I put arrows on the ends because I could go on forever in both directions. Now, the bottom says, what is one solution? So remember that on a line like this, any points that are on the line are solutions. So I have a whole bunch of possibilities that I could list. I'm going to pick one at random. There's a solution to that linear equation. It would be 6, 4, as the point. But remember, you could pick any one of those points, and that would be a solution to that equation. All right, good review from our Unit 2 that we just finished up. So now let's talk about what do we mean by a system of equations? That was just one linear equation. What is a system? So a system of equations is a set of 2 or more equations that have 2 or more variables that are solved at the same time. That are solved at the same time. So in that definition, I always said 2 or more. Now, we won't get too much into the or mores in this class. I will let you deal with that in Algebra 2 and beyond. But the idea of how you solve these could work for however many equations that you might have. But we will deal with really just when we have two equations that have two variables. So whenever you have a system, however many variables you have is how many equations you need in order to be able to find solutions. So if I have two variables, x and y, I need to have two equations in order to solve for specific solutions. If I had three variables, x, y, z, then I would have to have three equations to find specific solutions. So that's kind of how that goes, but we're going to focus on two only here. So then I keep talking about this, but what do we mean about solutions to a system? Well, a solution to a system would be any values that make both equations true. So it's not any values that would make either one true, and by true I mean that would work, right? Left side equals the right side. It has to make both of them true at the same time. So again, when we are talking about a set of two equations, that would mean that they have two variables, an x and a y. So I would have to have a value for x and a value for y that make both of the equations true. So when we're talking about two equations, we're really looking for a point, x comma y, that make both equations true. All right, so let's think about now if I give you a system. So this is what a system would look like. Notice I have two equations. Each equation has an x and a y in it. So this is what a system of equations looks like. And I'm trying to find a value for x and a value for y that make both equations true. And so graphing is one way to do that. Now I have to graph both of these lines on the same graph so that I can find a value that works in both equations. So I am going to take the space underneath my system here and I'm going to split it into two parts. This side, I'm going to pull this negative 5x plus y equals 0. That's going to be my space for doing work on that equation. And on the other side, I'm going to pull the bottom one, 5x plus y equals 10. And that's going to be my space for working on that equation. So I'm going to go back to the first one now. In order to graph this, I have to get y by itself, right? We're going y equals mx plus b, just like we did in the warm-up. So I'm going to add 5x to both sides. So I'll get y equals 5x plus 0. We could write plus 0. We don't have to write up plus 0. It's up to you, however you want to. Now I see, okay, from this equation, my slope is going to be 5, and my y-intercept is going to be 0. So I'm going to start my equation right here at 0, 0 on the y-axis, right? Y-intercept of 0 is going to start right there. And then my slope is 5. Remember, so rise of 5. If there is no run, put it over 1, right? So slope is rise of 5, run 1. So I'm going to go 1, 2, 3, 4, 5, and 1 over. Do it again. 1, 2, 3, 4, 5, over 1. I could go down 5, 1, 2, 3, 4, 5, and left 1. Same thing again. And then I have my line, right? Now, it's extremely important that you draw a nice straight line on this, and you will see why in a minute. So I know some of you are used to just making 2 points or 3 points and calling it good on your graph and drawing itty bitty baby lines. We tried our best to get you out of that habit back in Unit 2, but right now you're going to see why it's so important to draw lines that go all the way across your graph. There we go. Took me a minute to get it lined up. So there's my line for my first equation. Now I'm going to take a look at the second equation. This needs to get into slope intercept form as well. So I'm going to subtract 5x from both sides on this one. I'll get y equals negative 5x plus 10. The 5x was negative, the 10 was positive. All right, so now in this equation, I'll see that my slope is negative 5 and my y-intercept is positive 10. Begin with b up here way up top at 10. Okay. And then my slope will be a rise of negative 5. If there is no run, put it over 1. So I'm going to rise down 5, 1, 2, 3, 4, 5, and run 1. And oh, that's interesting. I'm going to do it again until I go all the way across my graph. There's the next one, 1, 2, 3, 4, 5, and run 1. 1, 2, 3, 4, 5, and run 1. Okay, now I have points all the way across. I'm going to get my ruler out again and draw a nice straight line here for this one as well. There we go. and then put arrows on the ends because it could go on forever. Now remember that I'm trying to find a value for x and a value for y that works for both equations. And now think, if it's going to work for both equations, it has to be on both lines, right? If there's a point on a line, it's a solution to that equation. If there's a point on the other line, it's a solution to that equation. So I have to find the point that works in both equations. Well, it's this point right here where the two lines intersect, right? So my solution to this system will always be a point, an x and a y, where those two lines intersect. So that would be at 1, 2, 3, 4, 5, at the point 1, 5. So my solution is always a point, and it is the point where the lines intersect. So I'm going to actually go back up here to my definition of a solution to a system, and I'm going to add in here the point, or maybe it's more than one, right? Point or points, where the lines intersect. That's how we'll know that it works in both equations. So you can see how a graph really helps us here. Okay, so let's go ahead and graph this one. Oh, look at that. This one they put in slope intercept form already. So again, I'm going to split my work in half, but not so much work to show on this one. Y equals x minus 3 is going on the left, and we will have, there we go. Nope, that's not the one I wanted. There we go. Y equals negative 2x plus 3 on the right. Let's go to our first equation here. So my slope, the invisible 1, right, would be 1 over 1. My y-intercept will be negative 3. So to begin at b at negative 3, rise 1, run 1, and this I can get a whole bunch of points all the way across my graph. Quickly, quickly, quickly. I could go the other way as well. And then I could draw a nice straight line. And you'll notice on the last problem, the reason I have to have nice straight lines that go all the way across my graph is I don't know where those two lines are going to intersect until I get both lines on the graph. So if you have itty bitty baby lines and it doesn't extend far enough, you might miss that point where it intersects. If you don't have straight lines, if they're real wobbly, then it might look like it's going through a certain point, but it's actually not. So that's why nice straight lines all the way across your graph is the most important thing here. So on this one, my slope is negative 2 over 1. My y-intercept is 3, positive 3 this time, so I'm going to start up here at 3. My rise is negative 2, so I'm going to go down 2 and run 1. Do it again, aha! But I'm going to still make sure that I go all the way across my graph, go the other way so I can draw a nice straight line all the way across. Okay, whoops. All right, close enough. Okay, so again, after I get my two lines graphed, I'm looking for that point of intersection that works in both equations. So right here it is, that point of intersection would be at positive 2, negative 1, right? Right 2, down 1. Okay, so remember, our solution to a system is always the point, x comma y. It's always going to be a point where those two lines intersect. All right, we've done it quite a bit now. Why don't you guys pause your video and see if you can do this one and find out what happens. So again, I'm going to split my work. My top equation is going to go over here on the left, y equals x minus 3. My bottom equation is going to go over here on the right, 2y equals 2x minus 6. Okay, top equation, looks pretty familiar, same as the last one. Invisible 1 for my slope, y-intercept is negative 3. Okay, and then rise 1, run 1, get your line all the way across your graph. Okay. And then draw that nice straight line. Okay, got that one. All right, now my second one, I need to do a little work. In order to get y by itself, I have to divide every single term by 2. So I get y equals, let's see, 2 divided by 2 gives me 1. You can write 1. You don't have to write 1. It's up to you. It could be just y equals x if you want. Negative 6 divided by 2 is negative 3. So my slope for this one, my slope is 1 over 1. My y-intercept is negative 3. Hang on. So my y-intercept is here, and I'm going to have points going all the way across all of these as well. So this is the exact same line. Well, if my solution is the point where they intersect, well, they're intersecting at every single point on that line. Well, how many points is that? Well, it looks like quite a few just on this graph, but remember that there's arrows on both ends. That is an infinite number of points where they are intersecting. So in this case, we call this infinite solutions. Now, when we had only one variable equations and we had this idea of infinite solutions, we called it all real numbers. Now, you have to be careful with that because you can't just say that any number you want is a solution here because it's only certain points, right? I can give you a point. This point right up here, that's not a solution to that system. So there are numbers that don't work. There are combinations of numbers that don't work. So we can't say all real numbers here. We have to say infinite solutions. It's not any number you want, but there's an infinite amount of them. Okay. And if I look again, I had infinite solutions because these were the same line. Or some people like to call these overlapping lines, however you want to think of it. When your lines are overlapping or they are actually the same line, whatever you want to think, we'll have infinite solutions. All right, let's look at this next one here. Again, ooh, that one's nice and easy, all set up for us. Why don't you go pause your video and see if you can graph it. All right, top equation going over on the left, y equals x plus 3. Bottom equation going over on the right, y equals x minus 3. On the top equation, my slope is that invisible 1. My y-intercept is positive 3. So here at positive 3, and then I rise 1 and run 1 and get a whole bunch of points this way. All right, get my line. There we go. Draw my nice straight line. Got it. All right, now the other one here, invisible 1 for my slope. My y-intercept is negative 3, though, so these are not the same line. I have to start at negative 3 and then put all my points, rise 1, run 1, and a whole bunch of points all the way across my graph like that. Okay, get my ruler out here, make a nice straight line. There we go. Well, now I'm looking for points where these lines intersect. But if I look at my graph here, hang on. Well, we would call these parallel lines, right? Parallel lines. Do parallel lines ever intersect? No, they're never going to touch. So we would say these are no solution. So when you have parallel lines, lines that never touch, then we would have no solution because the only way to have a solution is the point where the two lines intersect, and these lines never intersect. So we still have our infinite solutions, our no solutions, and then our one solution, right? There's our no solution, here's our infinite solutions, and then these other ones are one solution, right? Is there any way for two lines to touch in two places, but only two? No, that would be a curve, right? I'd have a wobbly line. That can't happen. So we can either have one solution. Now, one solution includes two numbers, right? X comma y, but that's only one point. So it's one solution. We could have an infinite number of solutions if the lines overlap. Or you can have no solutions at all if the lines never touch. So I made a little table down here just to help kind of remember what that is. So when we have one solution, again, remember, one solution has two numbers, x comma y. But those lines would be intersecting lines, right? That means they touch each other in only one place. All right, when we had infinite solutions is when we had the same or overlapping lines, however you want to think about it. Same line or overlapping lines. Then it would have an infinite number of solutions because they'd be touching in every single point on the line. And again, remember, we cannot call that all real numbers anymore. It has to be infinite solutions. And then our no solution, that was when we had parallel lines. Now, what I want to do in this bottom box is I want to go back and actually look at what our equations look like. What can we look for in our equations to know when I'm going to have parallel lines or when I'm going to have the same line? So when I'm putting them into slope intercept form, well, let's start with our no solution here, our parallel lines. Take a look at our slopes. On this one, our slopes were the same, right? But our y-intercepts were different. In fact, I might highlight it in two different colors then, get the idea, right? So one was positive 3 and one was negative 3, but our slopes were the same. So if I'm going to have parallel lines, I have to have the same slope, but different y-intercepts. All right, let's go up and look at the same line. I bet you could even tell without even looking at these again. But if we have the same line, our slopes were the same, and our y-intercepts were also the same. So if I'm going to have the same line, the equations would be the same, right? So that would mean I would have same slope and same y-intercept. All right, well now let's go back up and look at when we had one solution. So if I look at this one, my slope on this was 1, and my slope on this other one was negative 2, so different slopes. I also noticed that my y-intercept here was negative 3, and my y-intercept here was positive 3, so I had different slopes, different y-intercepts. Okay, on this one, same thing, right? Different slopes, different y-intercepts. So remember, if I have the same slope, then I'm either going to have the same or different y-intercepts. So I'm either going to have overlapping or parallel lines, right? If they have the same slope, those are my only options. So I definitely have to have different slopes. Do I have to have different y-intercepts? Well, just think about if two lines had different slopes but the same y-intercept. That just means that your two lines would be crossing at the y-intercept. So it would really still give you only 1 point for a solution. So the big idea for intersecting lines is they have to have different slope. If they're going to be intersecting, they have to have different slopes. But the y-intercept could be the same or it could be different. It doesn't matter either way. As long as you have different slopes, then you will have intersecting lines and you'll have one solution. Hopefully that kind of helps you wrap some things up, and then you don't always have to graph them if you can look for those kind of clues. Ooh, they have the same slope and they have the same or different y-intercepts. I know that they're going to have infinite or no solutions. Now, on your homework tonight, you still have to graph them because you have to practice, but in the future, you can have a little clue using this table. All right, so just to wrap it up, remember the solutions to a system is any point, x comma y, that make both equations true. So that's the point where the lines intersect. One solution, intersecting lines, will have different slopes, and the y-intercept could be the same or it could be different. If you're going to have infinite solutions, this would be the same or overlapping lines. They have the same slope and the same y-intercept because the equations are the same. And then if you're going to have no solution, that would be parallel lines. They would have the same slope but different y-intercepts.